Let us now study the steps in the design of columns subjected to axial load plus uniaxial bending. It is already told to you that for the column subjected to uniaxial bending, interaction diagrams are given by the special publication 16 of the IS code. You have to select the proper interaction diagram, and based on that interaction diagram, you have to arrive at the area of steel to be provided. Thus, the entire trial and error procedure is eliminated by the use of these interaction charts. Let us now study how to use these interaction charts for the purpose of design of the column subjected to axial load and uniaxial bending. The bending may be about x-axis, it may be about y-axis. Therefore, the separate procedure for both the axes is given. This is because when the bending takes about x-axis, the bending stress is equal to m by z, where that z is equal to bd square by 6, where when the bending takes place about y-axis, the bending stress is db square by 6. So accordingly, we have to understand the separate procedure. The procedure is exactly the same except replace d by b where it is bending about y-axis. So in this procedure for bending about x-axis, the data that is known to us is cross-sectional size of the column. This is to be assumed. What is the eccentricity about x-axis? What is the grade of steel, grade of concrete, and what is the axial load for which the column is to be designed? The question comes that what is the eccentricity on the column? Now two cases are possible. When the actual eccentricity is greater than minimum eccentricity of 20 mm, then we have to design the column for E actual that is equal to E actual. Therefore, we have to design the column that Ex equal to E actual. But when the actual eccentricity is less than minimum eccentricity, then we have to design the column for minimum eccentricity that is for 20 mm. Therefore, we have to calculate moment acting on the column equal to factored axial load multiplied by Ex. This Ex will be based on these two values. So if again I will repeat, if actual eccentricity is more than 20 mm, take actual eccentricity, but if actual eccentricity is less than 20 mm, you have to take it as 20 mm. So that will give us the minimum moment acting on the column. Now from this particular values of moment and the ultimate axial load, we have to arrive at the two quantities which are there on the y-axis and x-axis. Therefore, calculate Pu upon FCK BD and Mu upon FCK BD square. Always remember that here it is capital D. Nowhere effective depth is taken in the design of the column. And then you have to calculate the value of D dash upon D. What is this D dash? That is also given in the interaction chart. If you refer this particular figure, effective cover for the bars provided in the column, it is 40 mm plus half the bar diameter. So that gives you D dash. So this is D dash upon D. So separate interaction charts are available for 4 values of D dash upon D. That D dash upon D equal to 0.05, D dash upon D equal to 0.1, D dash upon D equal to 0.15, and D dash upon D equal to 0.2. So 4 charts are available, and based on this you have to select the proper chart for your D dash upon D value. It is quite likely that D dash upon D value may be somewhere in between of these two. Then you have to interpolate from these two values. Therefore, we have to find out the value of D dash upon D. Once this D dash upon D value is known, we have to select the proper chart based on grade of steel, because it is mentioned on the right corner of the chart that what is the grade, whether it is 250, 415, 500 accordingly. So based on grade of steel, based on D dash upon D, and based on arrangement of steel. Two types of steel arrangements are possible. Steel is provided only on two faces of the column like this, or steel is provided equally on all four faces of the column. So accordingly you have to select that particular proper chart. As I have already mentioned, D dash is the effective cover, which is equal to 40, that is the clear cover, plus half the bar diameter. Now you have to assume the bar diameter for calculating D dash. As mentioned earlier, in case of columns, the minimum bar diameter has to be 12 mm. Preferably assume diameter equal to 16 mm and proceed for calculating D dash upon D or 20 mm, so your D dash comes out to be 50 mm. Once you have these two values of Pu upon FCK BD square and Mu upon FCK BD square, based on these two values, you have to mark the point one on this axis, and where the interaction is there, you have to find out the value on that particular curve. So find the intersection of Pu upon FCK BD and Mu upon FCK BD square value. The intersection will give you the value of P upon FCK, which is written on this particular curve. On these curves, the values of P upon FCK are written, where P is the percentage of steel. Therefore, we get AS, which is equal to P into BD upon 100. This is the formula which is given on every interaction chart. It is mentioned in the right hand corner of the interaction chart. So you can use this formula, AS equal to P into BD upon 100. Therefore find out ASC. This is the longitudinal steel that we have to provide in the column. Based on that, you have to decide the bar diameter and bar number. Always take care to have minimum bar diameter as 12 mm and decide the number such that the distance between the bars should not be more than 300 mm. Once we decide this steel, you can design the links in the standard way by assuming the diameter of the link, deciding the diameter, and then the pitch of the link. This is the design procedure when the eccentricity of the column is about x-axis, that is when the bending is about x-axis. Eccentricity about x-axis means eccentricity is about the axis bisecting the depth of the column. In case of column, if B by D is the section of the column, always the axis that bisects the depth of the column is called as the XX axis or the major axis, and the axis that bisects the width of the column is called as minor axis or YY axis. So it does not depend on whether the column is oriented like this or whether the column is oriented like this. Even if the column is oriented like this will be considered as your XX axis in that case, and the horizontal axis will be your YY axis in that case. So when the bending is about Y axis, the same procedure is adopted, but now your moment of inertia is not BD cube by 12 but it is DB cube by 12. Therefore the value of Z also changes. So we have to calculate MUY equal to PU into EY, where EY is the eccentricity about Y axis, which is to be calculated in the same manner as we calculated for EX. In short, EY, if it is greater than minimum eccentricity, you have to consider actual eccentricity as EY. But EY, if it is less than minimum eccentricity, you have to consider EY equal to 20 mm. So you get the value of bending moment about Y axis. Knowing this bending moment about Y axis, now you have to calculate the value PU, direct stress, that is PU upon FCK BD. And now here there is a change because of the bending about Y axis. This is Mu upon FCK dB square and not BD square. Same thing here, the value changes. Instead of D dash upon D, as it is here about bending about X axis, now it is changing as D dash upon B. So understand the difference between bending about X axis and bending about Y axis. For bending about X axis, this is Mu upon FCK BD square, whereas here it is Mu upon FCK dB square. Here it is D dash upon D, here it is D dash upon B. So based on that, we have to select the proper chart. Once you select the proper chart based on the grade of the steel, based on the value of D dash upon B, and based on the decided arrangement of steel. Select the proper chart. So find, based on the proper chart, again you have to go and find the intersection point. That intersection point will give you the value of P upon FCK. As I have told you that this AS equal to P upon into BD upon 100. This is the formula given. Based on that you have to find out the area of steel required. So find out the diameter and number of bars satisfying the requirement of minimum diameter, maximum spacing, that is the distance between the bars. Once this is decided, you can have or you can design the links. Never a column is designed at the same time for bending about x-axis and bending about y-axis. Even the bending about both the axes take place at the same time. You have to design for one bending, that is for the maximum bending, and provide the same along the other axis, so that the steel will be maximum out of these two, and accordingly you have to design the column. Always in practice, the actual eccentricity is about one axis, as I have mentioned earlier. So the column is designed for the bending about major axis, and it is checked for bending about the minor axis. Vice versa, if the major bending is about y axis, the column is designed for bending about y axis, and it is checked for bending about x axis, which will be the minimum eccentricity. In any case, in practice, when you are providing a column of width 230 mm, it does not satisfy the IS requirement. That is why you have to design the column as subjected to uniaxial bending, and therefore you have to design the column for a minimum eccentricity of 20 mm if no, even if no actual eccentricity exists. Okay, so that finishes the steps in the design of the column subjected to uniaxial